Yamamoto from Keio University. We'll talk about system identification for linear quantum systems and spin networks.
Okay, thanks. It's a pleasure to be here. And unfortunately, there's no nice introduction about Tokyo. I'm from Tokyo, but maybe you can imagine that Tokyo is a complete opposite to Abyss Street, I guess. Okay, so this is I'm talking about the system identification. But before moving to the main part of the talk, I just would like to about the brief overview about the system identification. So here's, I guess, this is a most general schematic of system identification. So we have unknown system that we want to identify. And we have the known input that we can tune, we can design, we can engineer. And the output is that we can measure an output and we can have some information about the system from that output. So the goal of the system identification is this. Now, the set of input and output data is given to us by designing an input and measuring the output. But still, the system is not known. And the purpose of the system identification is using those data sets to construct the mathematical model of the system. Then the problem, in this case, the problem is called the non-parametric identification, because this is very important. To construct a mathematical model means that we do not know anything about the system. So that means system identification is nothing but the modeling method for the system, which is completely unknown and it's covered by the black box. But if we already know the mathematical model of the system, but it still contains some unknown parameters, then the problem is called the parametric model identification. So it is usually we thinking about parametric model identification, and in this talk we are dealing with this parametric model identification as well. So this is the most successful result in classical case for parametric model identification. The situation is that we assume that the system is we assume that the linear parametric model. So this is actually the assumption. So the system is followed by this differential equation, x out equal ax plus bu, and y equals cx plus du. So a, b, c, d are the matrices, which are unknown. So these four matrices, so we want to identify these four matrices. But these matrices are, in usual case, these matrices are very huge. For instance, 100 by 100, and so it contains many parameters to be estimated. So the problem is identify A, B, C, D using this input and output. And of course, it looks quite difficult problem because this has a huge number of parameters to be estimated. But there are a lot of nice methods in classical case to estimate, to identify those parameters, those matrices. And further, there are a lot of efficient methods for linear and even non-linear system identification in the classical case, and those basic problems.
What do you mean here by 1D? Do you mean that the matrices are three-diagonal?
I'm sorry, can you say again?
1D. System identification, sorry.
Sorry, this is identification. Sorry, yeah, this is abbreviation. Okay. All right. So this is actually, there are a lot of methods, and this is a famous book summarizing those specific techniques. Actually, the field of system identification in classical case is very, very well developed, and it is huge. It's a huge area. Right. We have seen that the classical case system identification is usually formulated in a dynamical input and output setup. X out equal x plus bu and y equals. This is differential equation. So this is dynamical equation. So we formulate. It would be good if we formulate the quantum system identification problem in the Markovian dynamical input and output setup as well, because then we can expect that some kind of nice method in classical case could be applied to the quantum case as well. And actually, this is true. So here's a typical setup of the dynamical quantum system, quantum input and output system. So here's a system, for instance, atomic ensemble, which contains some unknown parameters. And we inject a laser field which can be modulated, for instance, by EOM. So this is a non-input, non-modulating signal. And here's an output, and we can measure using, for instance, homodyne detection. So we have the output-based signal, y. So the purpose is to use u and y to identify the parametric this system, the parametric model of the system. Right. So I'd like to finally remark about the difference between the channel tomography and the system identification. Channel tomography is this is a typical setup of the channel tomography. And in this case, we just first at the initial state, initial time, we prepare the initial state, this one, and this evolves in time to the final state during some time. And at final time, we measure the system. And there's no measurement during this process, this dynamical process. And we got some measurement result. But this is actually the one typical measurement, one specific measurement result. We need to repeat the experiment. So before we got enough amount of the data for identification. But so on the other hand, this is a situation of system identification. As I said, this is the dynamical setup. So we have the time series of u and y. So here we are lucky, then only a single shot experiment is enough to get enough amount of the data for identification, if we are lucky. So those are very different. But I'm not saying that this system identification is better than the tomography setup. This is just the difference of the setup. Okay. So here's the main contents. In this talk, I'm talking about the linear system identification and non-linear system identification. So in the linear case, as we have before, there's a lot of nice result in classical case. So we can expect that those techniques can be applied to the quantum case, and it is actually true, and I'm demonstrating that thing. So on the other hand, the non-linear case, even the classical case, the situation is still ongoing, and there's no. Actually, there are a lot of efficient methods, but all of those, most of those techniques are heuristic, I guess. So we have to take a numerical approach to solve the problem. Especially in the non-linear case, I'm just thinking about the structure identification of spin networks, which is motivated by nitrogen vacancy center on diamond. So that's be a nice application to that specific scheme. Okay. First, I'm talking about the linear case. This is going to work with Madeline, and paper is already in archive and also in conference paper. Okay, so I'm talking about identifiability and specific identification method and the statistics related to quantum methodology like Fisher information stuff. Roughly speaking, those three topics correspond to what can we identify and how to identify and how much we can identify. So this is the whole procedure for system identification. Okay. First, I would like to explain the system. What is a linear system? This has already been explained by the Gufen, but I just want to repeat. So here's the system. The A is a vector composed of the annihilation operators, so n annihilation operators. So we have n set of n subsystems. Okay, so this is a network. And B is an annihilation process operator on the input field, and B out is an annihilation operator process on the output field. So we can measure this. And in the Markovian approximation and the Langevin equation is available, and this is a resulting equation. So A dot equals to be AA minus. So this is an input and this is an output. This is a system variable. And the situation here, A matrix is specified by this, has a specific form like this, and minus I omega minus half C delta C. And this omega corresponds to the system Hamiltonian. This is a Hamilton operator. And C is a complex matrix corresponding to the system field coupling. So there are 2 points. The system matrices have a specific structure characterized by omega and C. In the general case, of course, X dot equals AX plus BU and Y equals CX plus DU. So A, B, C, D matrices are the most general situation. But in this case, we have just two matrices characterizing the system. And the other thing is that input and output are solved by physical optical fields, not by abstract just a signal. In the classical case, we do not care about what is the physical state of the input and an output. But in the quantum case, it is a little bit it is actually important to think about the state of the input and output field, because this is the physical input and output. So actually, we will get some interesting observation on this point later on. So here's some examples. The typical one is optical resonator, which is used for the mode cleaning for the laser field. So then here A is an annihilation operator of the cavity field, the standing wave. The B1 is an input laser field, and here's an output. And also here's a B2, this is a vacuum input, and here's a bits out, which is mode cleaned. So I mean, in general, the laser field is pretty noisy, but this output is the noise level of the output field is reduced so that this is mode cleaned output field. So this is often used for optical experiment. And in this case, an omega is just a scalar. This omega is corresponding to detuning, and we want to estimate this value. And C is a coupling operator, coupling matrix, and in this case, the kappa is a coupling strength between the field and in the internal mode. Okay, so I just showing the second one. The next one is atomic ensembles, which is connected by the optical fields. So the A1 and A2 are the corrective lowering operators of the ensemble. So this is the approximation has already taken. This system also follows a passive linear quantum systems. And the interesting thing is that this is a passive system, and this is a Hurwitz in the language of control theory. So this is stable and going to be unique steady state. But that steady state is, interestingly, this is an entangled EPR state or two-model squeeze state. So this is in the dispersive regime. This system can be used for entanglement generation. And here, especially R is a parameter characterizing the entanglement level, which is called the squeezing level. So we really need to estimate the R, this value R, using the identification method. And omega is 0 in this case.
Excuse me?
Yes?
So you are doing quadrature QND measurement, or I should say quadrature QND interaction?
QND interaction, yes, yeah. No, at the moment, there's no measurement on the sources, but yeah. Okay, so here's a third example is taken from the field of quantum memory. The Lukens group's result. I don't give a detailed explanation, but anyway, so this system also follows the linear passive system, which contains various parameters to be estimated. Because in the quantum memory, we have to be very careful in designing, so for instance, mode matching or input field or some coupling, the tuning, something like that. So those parameters should be estimated very precisely, otherwise the memory fidelity is decreased a lot, so that we have to be very careful to estimate those parameters. And in this case, the omega is given by this, containing two parameters, and this is the coupling. Okay, so this is the last example. It's taken from the non-mechanical oscillator in the dispersive regime. So this is a little bit artificial in some reason that I'll show later. But here's a system matrix omega and C, which contains 4 parameters to be estimated. Okay, so those are the examples. So let's move on back to general situation. I'm just describing the problem. As we have seen that omega and C contain some parameters to be estimated, theta. So the problem of system identification is that we want to identify or estimate theta using the input and output data. So this is a system identification problem in our case. It's very simple, isn't it? Okay, so but in the linear case, we can take a very convenient approach in terms of the Fourier transfer function. So in the the Laplace domain, the input and output are connected by this very simple input and output relation. Here the LB is a Laplace transformation of B input, and LB out is the Laplace transformation of B out. They are connected by very simple relation. And here the QC is the transfer function matrix, or the matrix. Transfer function matrix, which is characterized by this one. So S is a complex number, and C and A are the matrices appearing in the system equation. So if the system equation is given to us, then we can define the transfer function uniquely. So this is a transfer function. So the point is that we can at most determine C, which contains theta, from only the input and output data. So our situation is that this is given to us, and this is also given to us. Then we can determine this QC from the input and output data. So this is a maximum information we can get from the data. Okay, so this is a problem. Now I'm describing the first topic in identifiability. This is an essentially the identifiable system is that its parameters can be identified in principle uniquely. Because this is very important, because if we know that beforehand that the system is not identifiable, then we shouldn't try to estimate the state. And precisely this is a waste of time, because the parameter should be identified uniquely. Otherwise, we shouldn't discuss about statistics or some kind of method. So this is a very important first step of the system identification procedure. The idea is already being given in a different context by D'Alessandro and Daniel 2 years ago. Okay, so what is the system identifiability? I guess again, we can at once determine the transfer function from only the input and output data. But a very important fact is that in the general situation, for the general linear system, which is a classical the quantum, any linear system, most general linear system. So this ABCD are the matrices we want to estimate. But this theorem falls to two minimal systems, ABCD and A prime, B prime, C prime, D prime, so different matrices, have the same transfer function if and only if there exists an invertible matrix T connecting those four matrices. You don't need to care about the word of minimal, but the situation is that so here's a system corresponding to theta, and if this theta is changed to theta prime a little bit, but if the two systems have the same transfer function, then you cannot distinguish these two parameters, so that this theta is essentially not identifiable. So this is a very important characterization of equivalent class of system that cannot be identifiable. Okay, so here's a definition. So what is identifiable? So if the two transfer functions corresponding to theta and theta prime are the same, then we can deduce the condition theta and theta prime. Then we call this parameter theta is identifiable. So again, this is a situation that we can at most determine the QC. So this is so we need some prior knowledge to satisfy the above condition, because there's no if without this prior information, this is the maximum information about the system. So we cannot go further to identify the system. And the prior knowledge is that because now we know that the system is passive quantum linear system, and we know that the omega matrix has some contains some parameters here, and this component is 0, or this component is 0. This kind of prior knowledge is useful to estimate the parameter.
One question.
Yeah.
You assume you can design any kind of input to system.
Could you say again?
So you assume you can design any type of input to
Specific time of input?
any type of input.
Now, I don't assume any state of the input, the single photon state or the coherent state, the squid state, input state, any state is allowed in.
So for this this definition, for some time input, okay, you may get the same state equal to the prime. I mean, for some other input, you may get a different state.
But the transfer function that doesn't depend on the input and output.
But in reality, you use input to identify your system, right? In practice, to design input sequence.
Input sequence?
Yeah.
I assume that the input is known, so we can design, we engineer any input. This is an assumption.
Yeah.
It has to be a sufficiently broad class, so you couldn't just have like sinusoids at a single frequency.
Right. Yeah.
Otherwise, not possible to do it.
Okay. Any other questions? Right. So, what is the situation? So we need some prior knowledge to satisfy above this condition. So what is an idea? So the region with color, with blue, this one, corresponds to the set of theta generating the same transfer function, which is called equivalent class. So if the parameter is here and this is parameter here, then these two parameters cannot be distinguished. So the parameter is not identifiable. So we should reduce the equivalent class using prior knowledge. First step is that we know that the system is linear positive quantum system. So we can reduce the equivalent class from here to here. So there's reduce the size of the equivalent class. And further, we know that the omega matrix contains some component here, 0 and 0, something like that. So this additional prior knowledge allows us to reduce the equivalent class from here to here. And repeating this procedure, we find that if we are lucky, we can get to this case where the parameter and the transfer function are in one-to-one correspondence. So if the transfer function is given to us, then we can identify the theta uniquely in principle. So this is the case where the theta is identifiable. Okay, so what is the equivalent class in linear passive linear quantum systems case? So this result is available through the similar procedure in the classical case. So the two minima quantum linear systems, omega. So now the linear quantum our system is characterized by omega and C. So the two linear systems, omega 1 and C1, and omega 2 C2, have the same transfer function if there exists a unitary matrix U connecting this omega and C. So in the most general case, the matrices are connected through simply the invertible matrix, which is size of 2n squared. But now we can reduce the size of the equivalent class to n squared minus 2n. This is a number of the components in the matrices. So this is a big reduction of the number of the parameters, Friedels. But of course, this is not enough to identify the system. So our definition of the identifiability becomes this. So that if these equations where the U is a variable, okay, so let me explain again. So if we solve this equation with the help of some prior knowledge about omega and C, and we can deduce the condition theta and theta prime, then we say that this theta is identifiable. This because this is an equivalent class. Because of course, and this equation depends on the specific system. So we need to go to the specific examples to see if the system is identifiable or not. We have seen the 4 examples specifically, and this system is identifiable. Okay, so this is identifiable, and also this is identifiable. But this is not identifiable because now you see that this is a very specific additional example, the 2 examples where the system is not identifiable. And actually, I had a lot of time to find this kind of non-identifiable system. So my intuition is that
Why not?
Because this is a very huge, this system contains the strong symmetry, right? So C2 and this is sorry, this is hidden, but this theta 2 and theta 3 are cannot be distinguished.
Same cavity with the two.
Yes. Anyway, so I think there are lots of many linear systems, partial linear systems are identifiable, I guess.
So I guess one issue, it depends on whether it's identifiable or not, may not matter, depending on what you want to use the model for. If you want to use the model to, say, design a feedback control system.
It depends on the model, so maybe
If you want to design a feedback control system, then it only matters what the transfer function is.
Yeah.
So even if you don't have the right parameters, you can still design the right control system. The same if you just want to simulate the system. If you want to simulate the input-output behavior, it doesn't matter what's going on inside. So you could. So it still wouldn't matter if it was not identifiable. It's only if you want to work out what's happening inside that you need identifiability.
You mean that we can design the system, modulate the system so that the system could become identifiable, you mean?
No, if it's not identifiable, there's a whole class of models which give you the same input-output behavior.
Okay.
But it doesn't matter which one of those you use if you're only concerned with the input-output behavior.
Right, yeah. So, yeah. All right.
Now, okay. Is the system here stable or not stable? This system.
Stable.
Stable.
Yeah.
Or not identifiable.
Stable, but not identifiable. So this is a very singular
Because
example.
it's stable, it must be controllable in party system and observable, right?
Yes, right.
So
Yeah.
it's not identifiable.
This is stable and observable and controllable, but not identifiable.
Yeah, it just means there's not enough information in the input-output behavior to determine all those parameters.
No matter what input you design, there's no way to.
Yeah, there's not enough. There's too many parameters compared with what information you get from input-output to exactly determine the values of those parameters.
Have design some other input, some.
Well, yeah, if you added some extra inputs and outputs, then it would change the system.
Right, yeah.
Good.
Yeah, you're right, yeah. Okay, so we need to solve some specific equations to check if the system is identifiable or not. So it should be good if we have a general condition that guarantees identifiability. Right, so this is a theorem. Suppose that the partial linear quantum system has an inflection property, then it is always identifiable, and we don't need to solve the equation. This is automatically identifiable. And this nice idea comes from the paper of Daniel and yours 2 years ago. So I'm just trying to explain the infection property. So here's an infected node. Okay, so this is an uninfected node. And if the infected node connects to the uninfected node uniquely, then this uninfected one can be infected. So okay, so these two guys are not unique to this one, right? So next, this one is uniquely coupled to the infected one. So this guy can become infected. And repeating this procedure, the whole network becomes infected. So then we call the system has an infection property. Is that the correct explanation, Daniel? No? There's no Daniel. It's gone. Okay, it's okay. All right. So essentially, the system having the infection property is essentially the same as a chain structure. It's a chain system. So it is not surprising that this kind of system is identifiable.
So is this some sort of graph connectivity property?
Yeah,
or?
yeah, true.
Points B,
Sorry?
in diagram B.
Diagram
I think
B.
you said it was uniquely connected to one of the blue nodes, but it's actually connected to two of them.
Oh, yes, yeah. This one is uniquely connected to this one.
And to the one down on the left.
Yeah, this one. Maybe I should say this does not have a unique uninfected node, but this one has a unique uninfected node. So this can become infected. And from here, so this node does not have the uninfected node uniquely, because this one is uninfected and this is uninfected. So this doesn't work. But from here, so this has an uninfected node uniquely. So from this to this, this can be infected. This is kind of complete topological connectivity property. So this is actually nice because we don't need to solve the equation.
So this is, I didn't really get, so this is the connectivity graph for the Hamilton, for the quadratic Hamiltonian,
Yes.
showing that which,
Yes.
which mode operator.
Yes. Yeah. Right. So let's move on to the next topic, identification method. So let's see the general situation. So now we have the input and output relation in terms of the in the Laplace domain. So this is the input. This is the input. This is an output, and we are this transfer function is given to us. So let's think about the single input and a single output case, and assume that the transfer function is constructed using the input and output data. And actually, this is possible to using some nice method in classical system identification method. Again, so if we are given the time series of input and output given to us, then we can reconstruct the transfer function from this relation. So let's assume this is given to us. So here is the C0 and the Cn minus 1, A0, A1, A2, An minus 1. Those coefficients are already determined using the input and output data. So this is given, and these coefficients are already determined. So here's a typical, so then if the transfer function is given to us, then we can reconstruct the dynamical equation of the system. And here's a typical one. So typical realization of the system dynamical equation is given by this. The good thing is that this A, B, C matrix is completely determined by using this coefficient A and C. So, but the problem is that, as I said, actually the transfer function and the system dynamic equation is not in one-to-one correspondence. There are many dynamic equations that has the same transfer function. So this is a typical specific choice of those infinitely many dynamic equations. And actually, this is very convenient, but these matrices not satisfy the quantum constraint characterized by omega and C, because for instance, this A, this B should be minus C dagger if the quantum constraint is satisfied, but it's not true in this case. So the problem is, so the question is, how can we reconstruct omega and C from this specific choice of the matrices, which is available from the input and output data? And here's an answer. This is a general case, not input and not SO case. This is a merge input and a merge output case. So first, A0 and C0 are given to us using the transfer function. And solve this equation. This is a linear equation, so that we can solve it effectively. And this solution X is diagonalized to this one, and we get U0 and lambda. This is a diagonal matrix, and U0 is a unitary matrix. And then we can reconstruct the omega and C like this. So, so here's a picture. So this blue plate corresponds to the equivalent class of the general linear dynamical equation that has a unique transfer function. So this is the equivalent class in the most general situation. But in our case, our system is quantum linear partial system, so that this is a subclass of this most general equivalent class, which is characterized by U. And this U appears here and here. So so we have the equivalent class in the that satisfy the quantum constraint. And then later we check the identifiability condition. We can determine the one of it, and this is the procedure for system identification. Yeah, that's all. Yeah.
Sorry, how is, so what is the U there? So I see that U naught is defined, but I'm not sure what U is.
U is any arbitrary unitary matrix.
Oh, it's in effect, okay.
Arbitrary, yeah.
Okay.
So this U generates a class of equivalent class for general linear partial systems.
So just before we go on to that, I guess another approach that would come to mind to me to solve this problem would be, we know that these passive systems have this all-pass property, the lossless bounded real property that Guofeng talked about yesterday.
Yeah.
And so then what you can do, and I think that's in the paper by Nina and myself, is you can solve the lossless bound. You can solve the equations in the lossless bounded real lemma to find the Archimedes matrix, and then you just need to diagonalize that to get back to the canonical commutation relations.
Okay.
So that just tells you a state space transformation that would transform you into the standard form, and then once you've got that, then this is formulas to construct the omega and the C from that state space realization. And it's probably pretty similar to, because that first equation you've got is actually the same equation as it is in the lossless bounded real lemma.
That's
So
interesting.
it's probably similar to what you're doing here, but not quite the same. So we can talk later just to
Right, I'll see it later.
What about non-passive systems? Because when you linearize nonlinear systems, they always end up being non-passive. So is this easily extendable to?
General one?
Yeah. Does it generalize to the case where you have a gain in the system?
I guess in this case, this U going to be a symplectic matrix. Yeah. I expect. Okay, so the final topic in the first part is the statistics, and we are talking about the Fisher information stuff. Okay, so this is a general set of quantum parameter estimation. So the talk is already given by Peter and nicely, so that I just give a result. So the problem is that we want to estimate the unknown parameter contained theta contained in our state. This is the case of the one parameter case. So the quantum Klein law bound is that there exists an unbiased estimate theta tilde satisfying this equality. And in other words, the estimation error is lower bounded by the inverse of f, where f is a quantum Fisher information, which doesn't depend on the measurement. This is the essential lower bound of the estimation error. So this quantum Fisher information is obtained by solving this linear equation. So here's an unbiased condition. So this is general situation result in the quantum parameter estimation problem. So in our case, we are interested in this problem. So what is the optimal input maximizing the Fisher information in the output? Here's a general setup again. Let's think about start from the standard case, whereas the coherent laser field with several amplitude and several frequencies. So here's the input. This is a separable state in coherent state with amplitude, several amplitude, Z1 and Z2, Z3, Zp, and omega 1, omega 2, omega 3. So we injected this coherent laser field with several amplitude and several frequencies. And the good thing in the passive linear system is that at the steady state, the system and the field are completely separable. So just we can look at only the output field state. So this is an output in the coherent field. And this is an amplitude. So the good thing is that this initial state, the Z1 corresponding to the initial coherent state is changing to this one. So this is the amplitude of the output coherent field, which contains QC, which is a system's transfer function. So we can get some information about the system just by measuring this output coherent field. And also, just let's impose the total energy on the input field. So Z1 is this is the total amplitude of the input field. So this is a nice, reasonable assumption, I guess. And E corresponds to the number of repetition in the quantum parameter estimation. So this E corresponds to this is N. Okay, so in this case, this is the Fisher information. This is the total. The Fisher information is the sum of the Fisher information of each input and output set, and this is the result. And especially because of the convexity property of the Fisher information, this takes the maximum value, which is given by this one. So this is an achievable maximum value of Fisher information. So we are interested in maximizing this value over the frequency and amplitude. So because this gives you an optimal input frequency. I'm not talking about the general situation, but let's think about the specific case study, whereas one-dimensional single input and a single output system, whereas omega is unknown parameters and C is fixed. This is non-constant. So in this case, the transfer function is given by this, and this is actually the phase shift which depends on the omega. So this is the dynamical phase shift depending on the input. Here's a typical situation, I guess. We are interested in estimating the frequency of the oscillator into this particular regime. So we want to estimate the frequency of the oscillator. And the question is, what is the optimal input frequency, and what is the optimal, and what is the best achievable accuracy, which is given by the 1/over Fisher information. So here's the input. Z is the amplitude, and omega is the frequency of the input coherent field. This is the output coherent field, which takes a phase shift depending on the theta. So this is essentially the phase estimation problem. But again, this phase depends on omega, so we need to optimize omega. Okay, so here's the result. This is the Fisher information. And the optimal frequency is given by this. Right? So but this is, of course, this is not unknown. So we do not know beforehand what is the optimal frequency, because the optimal frequency is given by the unknown parameter itself. But this is very natural in the sense that in the classical case, we need the M sequence. So this means that because our frequency and optimal input, optimal and unknown parameter, so we need the input with similar frequency composed of the many frequencies, and look at the output field and spectrum, power spectrum. And here's a dip corresponding to absorption. And this point gives you the optimal point. This point gives you the answer, the unknown parameter. So this kind of stuff. So I mean, the signal, input signal, which contains many frequencies, is called M sequence, maximum length sequence in the classical system identification. So as the usual recipe in the classical system identification is that we are advised to inject the M sequence in the system and look at the power spectrum in the output and see the dip in the spectrum. So this is a usual recipe in the classical system identification. But interesting is that this M sequence is now served by the coherent laser field, the physical state. It's not an abstract signal. This is a physical quantum state. And also, the other interesting thing is that this estimation error is lower bounded by this one. This is the inverse of the Fisher information. And this is fixed because the C is now known. And E corresponds to the number of repetition. And this is called the standard quantum limit. So if we have so if the mean photon number of the input coherent field is large, then the minimum is lower. So that's it is good estimate is possible because this is achievable. And also the C, this C should be small for the good estimation. And this C corresponds to the stability of the system. Because C is big, then the decay is rapid. But if C is small, then the decay is very slow and the time evolution is very slow. So we can have enough information about that time sequence. So there's an interesting trade-off between the stability and accuracy in the estimation. But all of the, like I said, all of this stuff is holds in even the classical case of the. So interesting thing that happens in the quantum case. If you take a exotic input state, like a noon state. Here's a statistical situation of generating the noon state. This is only the approximation, but combining the coherent state and the squeeze state, you can get the approximate noon state. Here's a so these two, the past two correspond to our principal, our system. And this one corresponds to the auxiliary system that we extend our system to the 1 and the 2, along the M1 and the 2. And this the parts of the noon state get the phase shift when acting on this system. So here's an input, and this is an output. So here's this part, whereas n is a photon number, acquires a phase shift gain obtained here. The point is that this phase shift is gains n here. So this is n times okay, so this n is a number of photons, so that if you inject a coherent field, this is simply minus 2I phi. But if you put a null state, it's going to be 2n phi. So as a result, we have the maximum Fisher information is going to be the E squared. But that means the Heisenberg limit, we can have the Heisenberg limit in the estimation error. And this is not achievable, I guess. So this is quantum methodology itself. And again, the optimal frequency is given by the unknown parameter theta. So interesting observation is that as before, we need the M sequence, which is composed of the many frequencies. But now, in this case, that M sequence is solved by a different quantum state rather than the coherent state. So in the classical case, we don't care about what state is used for generating the M sequence. But in the quantum case, we need to care about what state is used for carrying the M sequence. So this is, I think, an interesting difference between the classical and the quantum case, I think. Okay, so what's time? I need to hurry up to explain the second part. This is a nonlinear case. I'm talking about this system identification, structure identification of spin networks. The paper is on the New Journal of Physics. If you are interested, please look at it. So this is the motivation. So problem is, want to identify the limited access spin networks. So this is a very nicely developed network in nitrogen vacancy center in diamond. So this system is composed of electron spin in NV and nuclear spin in carbon around NV. And we can do some nice quantum gate operation or quantum computation like among this network using composed of the electron in the NV and the nuclear spin in electron carbon. So here's an issue. The issue is that only the NV is accessible usually. So if you scan the laser field on your device, then there's a flash point, and you can detect here's a NV. But the carbon atom generated randomly in usual. So that means that the structure of the system composed of NV and C is unknown usually. So that's an issue because we want to do some nice gate operation on the whole system composed of carbon and nitrogen NV. So this is a system setup. We consider the spin network composed of the XY type interaction Hamiltonian, which is given by this. So XX and YY, and there's no Z component. And lambda JK is the coupling strings between the J's node and the K's node. So if lambda JK is 0, that means the J's node and the K's node are not connected. And also we are allowed, so this is the assumption, we are allowed to measure only a single node like an NV center. This is accessible node we can measure. And the other assumption is that we can perform, this is an assumption, we can perform a continuous measurement of sigma Z of the accessible spin using, for instance, this kind of a hybrid nice structure composed of an NV and the graphene like oscillator stuff. But anyway, this is a time evolution of our conditional state. So this law, this is a second master equation actually. So this law describes our knowledge based on our measurement result. So if we get measurement result Y, then we update our state. And repeating this procedure, we can get more information about the system using by processing this equation. So this is actually the classical differential equation, stochastic differential equation, describing our knowledge. And here, this C is given by this, which means that we can access only to the first node. And this is a dissipation term, and this is an innovation term. And here's the gamma is the measurement strings, and the is the standard Wiener increment. And the purpose is to, now our system is computed in the black box. So we want to open it up, and we want to know the structure of the system. Okay. So, but this problem is too difficult to solve. So we need some assumption on it. Because this lambda JK is unknown parameters, but it's too large because we do not know the structure and we don't know the number of the network. So this is too difficult problem. So we need some assumptions on it. The last one is that lambda JK are all distributed around the known value lambda. So this is distributed around the known value. So if for instance, if the lambda is given by 1, then the true structure is connected by with strengths like 1.1 or 0.9, something like that. But we don't know the exact value of the coupling strength. The other assumption is that the maximum number of the nodes is known. For instance, the maximum is 10 nodes are connected with each other, or something like that. So, and here's an important note. So if we can identify the structure, then lambda jk can be estimated by using the method developed by Daniel. So this would be a nice combination. Just we first identify the structure, then using the Daniel's method to estimate the coupling strengths. That would be a nice combination, I think. Okay, so here's a procedure to solve the problem. So choose the true graph. So the I0 means that we have the true graph. But because we do not know the true structure, we need to prepare all the possible candidates for the graph structures, which is D1, D2, D3, Tm, which is a huge number of the. Okay.
Can I make a comment? So for MB centers, usually the electron spin couples to its neighboring nuclear spins. It's like a central spin model.
Yeah.
So you kind of have some prior knowledge about the structure.
Okay, so actually, yeah, the NB centers one is actually the motivating thing. This is not a different situation. Okay.
Okay.
Yeah.
So it's more general case.
Right. Yeah. So this is the case of the maximum number of the node is 3. So we know that maximum number of the system is composed of only 3 nodes. So in this case, there are 5 candidates describing the structure. So this is the case where all nodes are connected with each other. And this is the case, only 2 nodes are connected with each other, and another one is not connected to these 2 guys. And this is the case where the accessible node is not connected to the other guys. So we have these 5 candidates and update our knowledge, which one is correct. So here's the procedure. I don't explain about it. But the basic idea is that we update our knowledge based on the base update. So here's the result. We update our state as well as our knowledge about the candidates of the graph structure. So this is a hybrid stochastic master equation, updating our knowledge about the state and also our knowledge about the candidates or the structure. So this is a stochastic master equation describing the state and knowledge. Right? So this is a situation describing the picture describing the situation. Okay, so here's an example where the maximum number of nodes is 3. So here's a time 0, and we have 5 candidates, 1, 2, 3, 4, 5. And we don't know anything about it at the initial time. So we have to set the uniform distribution on about structure. Okay, so 0.2 is the initial state distribution in the classical probability density describing the structure. And by getting the information about the system, we can update our knowledge and going to be true value corresponding to the true structure. Okay, so in this case, this is a true structure, and this is an estimated structure. So it works. And here's a typical physical interpretation, where actually we are just, because the Z component is not preserved, so that we are just observing the edge of the network, the spin wave. So because the Z component is preserved, the spin waves occurs in the network. So if maybe the next one is good. So if if the network is pretty long at the chain structure, then the wave is coming back like that. But if the structure is connected more closely, then the spin wave comes back more quickly. And if the structure is rather something like this, not connected to other nodes, then there's no spin wave. So that we can distinguish these 5 candidates just by using the measurement results. So this is a physical interpretation. So lastly, I just skipped a bit hurry up to show the result in the 5 nodes case. Here's a case where the spin chain, the chain structure is a true one, and we want to estimate this one. And here's the assumption is that lambda jk is distributed around the known value 1. Okay, so here's a uniform distribution is going to be the true one, so that it works. But and this is if the true structure is given by this one, still it's going to be the true one. It works as well. It's still some wrong answer appears here, but in this case, it doesn't work because maybe this structure is hard to distinguish. So maybe they are indistinguishable, I guess. This doesn't work as well. So if the true structure is given by this, then because we cannot distinguish, I guess we cannot distinguish these two graph structures, then because so therefore the trajectory is going to be not uniquely converged. So I guess my interesting, this is as well. The interesting question is that if the system is identifiable, we can distinguish all the graph structures, then maybe the convergence is unique. I don't know the answer. So anyway, so this is a summary, and thank you very much.
Thank you, Naoki. So some questions?
Yes.
So I noticed there that you were using XY coupling of the spins.
Right.
In principle, you could think about any sort of coupling to the spins. Do you think that would affect the
I've not tried that. This is a very simple case where we can get physical interpretation like a spin wave.
In the metrology case you outlined, you framed it in terms of the quantum Fisher information.
Yeah.
So there's an implicit assumption, I suppose, that you can actually realize the POVMs that will saturate that band.
Mm-hmm.
So my question is, for the linear systems that you set up, is that always true because it's essentially a Gaussian system?
Yes.
Okay. So in that case, when you use the noon state, of course, that's no longer a Gaussian input state. Is it clear that one should always use Gaussian measurement to maximize that Fisher information?
Yep. And I don't know the answer, actually. That means the classical Fisher information could be achievable to the quantum information using some clever measurement, but I don't know how to realize that.
I'm surprised that the last example you gave, that the star with 3 and the star with 4 is indistinguishable.
Yeah.
Shouldn't you just be able to kind of measure the number of frequencies in the Fourier spectrum, and then you know how many there are, or is there some kind of degeneracy issue that
using your method, maybe.
For example, yeah, but I mean, just a very naive approach should tell you how many spins there are around. Unless there's some degeneracy in the eigenvalues which we don't see, but do you know what?
Sorry, I don't know actually.
I think for that maybe there's a dark mode.
There are lots of dark modes, but the number of dark, I mean, so it's surprising that the spectrum would be exactly the same component.
Maybe the dark mode is completely decoupled from your readout.
Yeah, no, it's clear the dark modes you don't see, but still, when you go from 3 to 4, I expect that there's at least one more bright mode compared to the 3 case.
Maybe add one more dark mode, then you can see it.
Okay,
maybe.
So this is just a sort of formal question, I suppose, which is, given the system identification results that you have now, it seems to me you have the tools to construct an S, L, and H given any transfer matrix. Is that a fair assessment?
It's a general case, general situation.
Of course, I gave you transfer matrix, so I assume it's linear.
But
otherwise, yes, that's my question. Is that really where we are, or is there something missing?
Your question is, what I understand is that it is always true. It's always possible to reconstruct the transfer function with input of data corresponding to the SLH model, because the SLH model uniquely corresponds to the transfer system equations, omega and C.
Yeah, so I just want to make certain that there's no holes. Yeah, so for example, you have a certain assumption about your scattering matrix, transfer matrix, that the number of poles is countable.
Okay. Important assumption is that the system is minimal. So if the system is not minimal, it is not possible to identify the transfer function. Am I answering correctly?
But
There was a slide about the realizability of this. So if you are given the transfer function, how you construct a system which has that transfer function.
So in general, for a given transfer function, there'd be a lot of SLHs which would lead to the same transfer function as well.
Yeah, but that's not the question. I guess the question is, when does it break? Like if I, for example, at the moment I've taken transfer functions which are implicitly meromorphic, so it's a set of poles, but I don't have a branch cut. So what happens if I have a branch cut in my transfer function? Does that change the outcome?
What is the branch cut? I'm sorry.
It's a compact dense set of poles.
Okay.
So it's infinite dimensional transfer, non-rational transfer function.
Yes, that's right, not much.
Okay. Sorry, I'm not a good answer. Sorry.
Okay, no.
Well, there is an underlying assumption that the system has a finite number of nodes.
Yeah.
You need an infinite number of oscillators to produce.
I mean, this is true, but I was trying to understand what other things break. That's one example.
Yeah. Right, more questions? So if not, let's thank Naoki and Daniel again.
Just make a quick announcement.